So 11.6, we're going to do the homework. But I noticed this time around, the second edition homework was actually different enough from the first edition homework. So
it was a lot different.
It's not the end of the world, but there are some problems that I wanted to emphasize that the second edition didn't emphasize. So for example, 37 in the second edition was actually like this thing you have to use a computer program to do.
Yeah.
Obviously, I wouldn't have assigned that. The problem in the second edition, which would more match with the problem I gave in the first edition, would be 39. That would more look like 37 from the first edition. So for the benefit of those who did the homework from the second edition, I think I should go through one of these problems.
That's a very good idea.
Either 37 from first edition or 39 from the second edition. They're slightly different, but it's the same kind of problem. Maybe I'll do the first edition. Or do you want the second edition?
Second edition.
You want the second edition?
The 1.5 edition.
Wouldn't that be 1 3/4?
First edition, number 37. So this gave us a function. So this would sort of be equivalent to, for those of you who have the second edition and want to extra practice, you can practice 39. If I'd renumbered the exercise, I would have assigned that for the second edition. So this would be x squared plus 4y squared. It said find the gradient vector at the point 2, 1. Use it to find the tangent line to f of xy equals 8. Sketch the curve, the tangent line, and the gradient vector. Right, so in the second edition, they gave you a different function at a different point, but everything else was the same. So if you know how to do this one, you should know how to do that one. Okay, so
They
let's
wanted
do
to
this.
sketch the curve and the tangent line?
Sketch the curve with the tangent line and the gradient vector, all on the same graph. Okay, so how would we start here? First, can find the gradient vector, which is, what's the formula for it?
F sub x, F sub y.
Okay, the partials. All right, so the gradient here, it's equal to
2x. AY.
8y. Right? So then your gradient vector at the point 2, 1 would be the vector
4 and
4, 8. Okay, so we have found that. Check. How do you find the tangent line to this? Right, so want tangent line to x squared plus 4y squared equals 8. What kind of curve is that?
Ellipse.
Parabola.
Alex.
Looks like, wait, it makes one word, so send it.
So I'm hearing a whole bunch of Okay. Why is it not a circle?
Because of
Because of the 4, right? You have to have the coefficient of the squares be the same one. Why is it not a parabola? Both of these are squared. You have to only have one square to be a parabola, right? These are things that you should recognize pictorially at this point, like just by the symbols on the page, right? It's an ellipse. How do we find the a nice form so we can graph it?
Divide everything by 8.
Divide everything by 8, so you get x squared over 8 plus y squared over 2 equals 1, right? So now it looks like the form of an ellipse. So it's actually an ellipse, right? So we know what the sketch is going to look like. But we want the tangent point to this curve at this point, right? And they said use this guy to help us. So how do you think we're going to do that?
With a calculator.
You can actually do it like you would do the tangent plane, except you just leave off the z part. So that would give us, so the tangent line at 2, 1 has the form fx times x minus 2 plus fy times 1 minus 1. So this gives us the tangent line 4 x minus 2 plus 8 y minus 1. That's actually the equation of the line. 4x minus 8 plus 8y minus 8, 0. 4x plus 8y equals 16. X plus 2 equals 4. That's actually the equation of the tangent line. And so now let's do the sketch. So here it's stretched more along the x than the y, so it looks like this. What's this point here?
That's X.
Root 2, 0?
No,
No, I'm
4.
sorry. 2 root 2, 0.
2 root 2. On the x, so this would be minus 2 root 2. This would be root 2. That would be root 2
Yeah.
minus. And the point 2, 1 is somewhere like over here. And so our line would, our tangent line would look like this. And then, of course, this vector would be orthogonal to that. That would be the sketch. Right? And you can even try, you can realize here that this guy is actually minus x over 2 plus 2. So you know it has a negative slope. Your y-intercept is actually 2, which is a little bigger than radical 2, so your picture is sort of indicating what you found. Yeah, but that's a nice type of problem, but I don't think the second edition had any problems like that.
39 looks like it.
39, but it wasn't assigned. 39 wasn't an assigned problem. Yeah, there's an equivalent problem which is 39, where they gave you the function xy, right? And they said you should graph it at the point where f of xy equals 6. So if you have xy equals 6, how does the graph look?
Y equals x over 6. So it's going to
Y equals 6 over x. Right, so how would that look? Right, like that. Right, so, and they gave you a positive point, so you were talking about over here, so your picture should sort of look like that for the second edition version from. Okay. Other than that, I think the essential ground was covered, but I'll take questions on whatever you want, if there are other questions. In the first or second? Okay, that's fine. minus 2x minus 4y. Find points where direction of fastest rate of change is I plus j. Okay. Can someone express in other words what they are asking us for?
The direction of the fastest rate of change is the direction of the gradient vector.
Correct.
So if we find the gradient vector and we,
So you want all points where the gradient vector has what property?
it's equal to 1, comma, 1.
Not necessarily equal to, parallel to.
You're right, okay. Favorable. Right. Good point.
Right, so asking for this is exactly the same as asking for that, right? Because we know the direction of maximum increase, maximum rate of change, is the same direction as the gradient vector. That was a theorem we had last time. So they're really asking, what points does this happen, right? Where is the gradient vector actually parallel to that vector?
It wouldn't
So-
have to necessarily equal the unit vector.
No, it won't have to be equal. Because there's no guarantee that this has magnitude of that. Right?
Okay.
So let's first do gradient f, which in this case is what?
2x minus 2.
2x minus 2. 2y minus 4. And we want 2x minus 2, 2y minus 4 to be equal to what?
Or AA.
AA or KK, a constant times this vector. Right? So that means your 2x minus 2 is equal to k, but also your 2y minus 4 should be equal to k. This implies 2x minus 2 is equal to 2y minus 4, and those are all the points. So I can x minus 1 equals y minus 2, or x minus y equals minus 1. So all points on this line, we have this parallel. Okay, that's it. So we put this constraint in effect, and as a result, we got a line. So it means that every point on that line, the maximum rate of change will be in a direction parallel to this one. Other questions?
45.
It's a circle, no, it's a problem.
Are you making fun of us?
What does the normal line to the paraboloid at the point? Where does it intersect the second time? You said 45, right?
Yeah.
Second edition. So we have f of x, y plus z. X squared plus y squared. Where does normal line at 1, 2 intersect the surface of it? So here it is. We have this paraboloid thing going on. There's a point here which I can call 1, 1, 2, and I drew a normal line to that guy, right? But then that line is going to continue. It's going to puncture the thing somewhere else. I want to find that point. That's what they're asking. So we know one of the points where it cuts through the thing is at 1, 1, 2. Find the other point. That's the question. So how do we do that?
I find the equation for the line first.
First find the equation for the line, and then you
Parking.
substitute it in the points, right? So how do you find the equation for the normal line?
Find the rank.
You need a point and a direction for a line, right? So we already know the point is 1, 1, 2. The direction is
2x, comma, 2y, which is going
right.
to be 2.
It's the gradient that you're at the point.
It's going to be 2, comma, 2.
Right. So this is going to be 2x,
2y.
2y.
Negative.
Negative
Yeah.
1.
And it's evaluated at the point 1, 1, 2. So that's just 2 minus 1 is the direction. So this means normal line is that means your x is equal to 1 plus 2t. Your y is equal to 1 plus 2t. And your z is equal to 2 minus t. So if the equation z equals x squared plus y squared becomes, place this with 2 minus t, and this is 2 times 1 plus 2t squared. Now you just solve for t. So we have 8t squared plus 9t. And then that's just equal to 0. So t of 8t plus 9 equals 0. So you have t equals 0 and t equals minus 9 over 8. Now notice that when t equals 0, you get the point that it intersected first. So
Right.
the t equals minus 9 over 8 corresponds to the other point. This corresponds to second intersection. This corresponds to 1, 2. So this means the point that we care about is here. Just plug in 1 plus 2 times minus 9 over 8, comma 1 plus 2 times minus 9 over 8, comma 2 plus 9 over 8. And what's that?
Negative 5 over 4.
Minus 5 over 4, comma minus 5 over 4, comma
25 over 8.
25 over 8.
Yep.
What does that say? This corresponds to?
The
Oh, second
intersection.
Can you number 23, please? Second edition.
Let's see if that's relevant there on the
Yeah, that's okay. A similar problem is also in the first edition. I don't know if it was the same problem, but the same number, but it's the same. It's probably 25 in the first edition, I'm not sure. So we have the temp t in a ball inversely proportional to distance from the center. T equals 120 at the point 1, 2, 2.
Center is the origin, that way?
Yeah, so we can think of the ball as being centered at the origin, that's fine. The rate of change, so it's talking about directional derivative, but we need to know what the formula for t is. What does inversely proportional mean?
As one gets bigger, the other gets smaller.
Right, give me an equation. X is inversely proportional to y if y is equal to
1 over x.
K over X.
k over x, a constant times 1 over x. Okay, so now they're telling us here, they're telling us the temperature is inversely proportional to the distance from the center. And what's the distance from the center of a circle, of a sphere?
Square root x squared plus y squared.
Right, it's just the radius.
Yeah.
So it means that's the formula that you're going to do this problem. So remember, the distance from the center is just the radius. Right, so if you think of the ball as being, you know, x squared plus y squared plus z squared equals r squared, then this is what we're looking for, and that's that. So that's our function, and we're going to use that as, I guess, so we want a directional derivative. How do we find that? It's going to be the gradient, so the directional derivative would be the gradient of t dot product with some direction that we want to move in, right? So the gradient of t is going to be what in this case? Negative kx over what?
All of that to the 3 over 2.
And what is u?
U would be the unit vector of the vector we were given, which is 1, 1, 1.
Where were
Oh,
we
wait.
given 1, 1, 1?
That's one. You give you 2 points, you can find the vector.
Right, so this is your initial point.
1 minus 1, 1.
And this is the final point. So you can actually find the direction. So it's 2 minus 1. 1.
Minus
and then
1.
you can do, minus 1.
And 1.
And then 1. But
Is
then
ne- is
you
that,
want-
that's not a unit vector, is it?
this isn't the unit vector,
Okay.
no.
So what?
So we have to
then-
divide by its magnitude,
Which is root 3.
which is radical 3. Right, so that's your general formula, and we want to find it at this point specifically. So we just plug in 1, 2, 2. So directional derivative of t at 1, 2, 2 is equal to, what does this guy look like? If I plug in 1, 2, 2. This is actually 9, right?
27.
Square root, so this would be 27.
Over
And so this is
K.
minus k, x is
1.
over 27,
Right.
Minus 2k.
minus 2k over 27,
2k.
minus 2k over 27, dot product with 1 minus 1, 1 over radical 3. So what does that look like? So it's just going to be minus k. Well, I can put the 1 over radical 3 on the outside.
I have a question.
Yeah.
It says inversely proportional from the center, but this is going from 1, 2, 2 to 2, 1, 3. It's not going. How do you know what if it's traveling to or from the center?
Oh, that's to the center is part. What do you mean? You're asking about what?
The formula we have there for t.
Yeah.
That's from point 1, 2, 2 to the center, right? From the center
No.
1, 2, 2.
Nope.
Temperature is at the 1, 2, 2.
It's saying if you're within this ball, then no matter what point you're at, the temperature at that point is going to be given by that formula for some constant k.
Well, you can find
So-
the k by the temperature 120 and the point 1, 2, 2.
Yeah, we could find a k.
So what's the connection between 1, 2, 2 and 2, 1, 3?
No connection whatsoever. Like not like goes towards the center or anything like that.
So why is it giving us 1, 2, 2? Why don't we just use 2, 1,
So
3?
it's just saying we're at one point in the ball and we want to move to another point in the ball. How's the temperature going to change? Is it going to get hotter or colder? That's basically what they're asking.
Okay.
Right? Now the temperature, you know how it's measured if you're coming from the center, but what if you want to go somewhere else? How do you know how the temperature is going to change then? Right? So you know it's sort of hotter in the center and colder on the outside, but then what if you're traveling on the outside? How's the temperature? Right? It's sort of expanding on using what you know to figure out what you don't know. Sort of the expansion. And yes, like as Yufeng said, you could actually find k here using this point. I thought I'd solve it in general, but you can actually do that. So you can actually plug in the 120 for, right, like here. You plug in 120 for t, and then plug in 1, 2, 2 here, and you can actually solve the k. Would you prefer me to do that?
No.
You don't want to do that.
I mean,
We have an example.
the find k, we know that t at 1, 2, 2 is equal to 120. This means k over 27 is equal to 120, so k is equal to 120 times 27, which is like whatever. What is it?
It's not 27.
It's
It's 3.
It's just 3. Right, because that was to the 3 over 2, that's why it was 27. Okay, that's nice.
360.
Where did you get the 3 from?
That's 1.
The radical of x squared plus y squared plus z squared. Plug in 1, 2, 2. That gives you 9. You take the radical, you get 2. I cubed it to get 27, but that's done. Okay, so this would be minus 360 over 27. So we'll actually get a number here. This is going to be 1 over radical 3 times so this would cover that. So this is just minus 360 over 27 radical 3. And that can simplify, right? Yeah. What does it simplify to?
Negative 40 over 3.
Right, so your temperature is actually decreasing if you move from that point to that point. But you could also look at it as you can sort of you can tell which point is the towards the center. The distance is closer to the center by this roundabout way if you want to. So now part B. Show that the greatest increase in temperature is towards the origin. How do I know where the greatest increase in temperature is?
Wait, where'd you plug in the 213? You only found the first.
Oh, I used that to find this here. What do you plug in the 213?
I thought we were supposed to.
Oh no, the 213 you used to get the u. That's where that came in, right? You only plug in the base point, right? This final point just helped us to find the vector, but everything is evaluated at the base point. Right. So you're evaluating all your functions and everything you're plugging in is where you're starting from, right? The second point just helps you to find the direction you're moving in, right? So once you use that here, we don't really need it again. How do I know the greatest rate of increase is towards the origin?
Okay, that's a big deal. Same direction.
Same direction.
Direction of, how did they phrase it? Greatest increase. Is this guy, just right, which we actually have a formula for, right? Notice that we can write that as something like is that basically we can simplify this guy to look like that, right? The radical of x squared plus y squared plus z squared is actually the radius. And so the denominator is just the radius cubed. I can factor out the constant. Remember that k is positive, which means that this thing here would be a negative number. So we have a negative number times this vector, but what's that vector? It's just a position vector that gives you the point x, y, z. Right? So that vector is just going to be the vector that starts here and goes out to a point x, y, z. Right? That's that vector, x, y, z. But then we're taking the negative of it, which means our vector is going
0 minus x.
0 minus x.
Y.
Tell me why you keep the radius.
Because of here. Right? X squared plus y squared with z squared to the half is the radius. And then there's a cube here. I just didn't want to write out x squared plus y squared with z squared. I wrote r instead and moved it out. Other questions?
47.
Second edition, first edition?
Yeah.
Huh?
First edition.
Do you want the first edition on that?
No, I haven't. Okay, maybe we'll end here. So no one had questions on finding equations of tangent planes? That was just easy. Yeah, that's how it works. They make you suffer for something, and then they teach you something where it's like, oh, that was just too easy. Just like implicit differentiation. Well, why did we do all that in Calc 1 and 2? Why couldn't they tell us about partial derivatives back then? Everything would be so much easier. Two surfaces are orthogonal if their normal lines are perpendicular at the point of the surface. This and this are orthogonal. Okay, so one thing to do. So remember, so for f of x, y, z equals 0, direction of normal line is what? The gradient. The gradient. That's the whole point of the gradient. It actually gives you the orthogonal direction to the surface that you're on. Right? So now, if f, so it says, what does it say? Show that if two surfaces are orthogonal, so if f equals 0 and g equals 0 are orthogonal, then, now we know that two things are orthogonal if their normal lines are orthogonal. So how can we tell if these two vectors are orthogonal?
Dot product 0.
Dot product is 0. It means that the gradient of this guy dot product with the gradient of that guy equals 0.
Which is just what they wanted us to do.
Right, but that just means partial with respect to x, partial with respect to y, partial with respect to z, dot product with partial with respect to x, partial with respect to y, partial with respect to z equals 0. That's just fx gx plus fy gy plus fz gz equals 0. So they wanted us to show. This is in the first edition. Use priority to show that this and this are orthogonal at every point of intersection. So now show that z squared equals x squared plus y squared and x squared plus Okay, so how do we do that?
Gradients.
Find the gradients.
Well, first, I guess we define them
Yeah.
as,
Let me call f to be this surface, x squared plus y squared minus z squared equals 0.
right,
And my g is the x squared plus y squared plus z squared minus r squared equals 0. Then my gradient of f is going to be
2x.
2x, 2y minus 2z. And this will be 2x, 2y, 2z. This means if I take their dot products, I would get 4x squared plus 4y squared minus 4z squared equals 4x squared plus 4y squared minus 4x squared plus y squared. Right? I can replace z squared with x squared plus y squared from this one. Right? And I know that doing that will also work here because I'm at a point of intersection. So I can assume that the z's coincide. So I can just use the z for here as the z for everything. And that actually gives you 0. And it did not depend on the x, y, and z I used. So this did not depend on x, y, z on particular x, y, z values. So they are orthogonal. At all points of intersection. Can you see this without calculus? Who could have figured out the answer without any calc 3? Euclid could, that's right. Comes from the picture. One is a sphere of radius r. The other is a cone. The interesting about a cone is the edges are straight lines. Right? So if you turn this into a geometry problem where you just have a circle and you have a straight line that passes through the origin, it will always meet here at orthogonal, right? No matter what. Right? The radius is always orthogonal to the circumference of a circle. Right? But here we have a calculus 3 way of saying that. Okay, so bring up your homework. We'll take a 10-minute break and then we'll try to finish chapter 11. Didn't even finish chapter 11. Why even yeah, but a lot of the problems you don't even know how to do yet. So I didn't teach you. What do you mean? I didn't teach them. You didn't finish it last time.
No, they didn't give me one chapter.
One section.
Semantics.
没有啊，昨天没讲这里的主要，没这什么地方嘛，分很多大小，都挺好。
Your butt's dry.
This here?
Imagine what we're thinking about.
can start recording.
You're gonna say-